Okay, now we are going to talk about replacement policies. That means we are going to talk about cache replacement in detail right now. So let's see here. In direct mapped cache, there is a unique mapping. That is, in direct mapped cache, we know each address is mapping to exactly one unique block and set, right? So therefore, if you see, every memory address we know has exactly one place it can go into. So there is a no choice. We don't need to decide. So each memory block is assigned to one specific cache slot, that is block. So therefore, if you consider here in our direct cache, there are each blocks, right? Now when you consider each of this block, the data is supposed to go, that is, if you have one memory address, it is supposed to go to only one set. So what happened is that when in such cases, when conflict occurs, right, sometimes conflict can occur, both addresses matching, then we have to replace the previous one and put this. That is only thing that is happening in direct map cache. So in direct map cache, in replacement, if you consider, there is no choice. Since each address mapped to only one location, when a new data needs to go there and something already occupies the spot, the existing data is unconditionally evicted and no decision. Here, the replacement that is used in the direct mapped is that only one data can go to one block. Right, so this is my direct mapped cache. So only one data can go to one block. So if let's say in this block there is 2, another memory address data 3 has to come to the same block itself. So that means the only choice is to evict this 2 and put this 3. There is no other replacement that is used here. Again, if I want to add any 4 which is coming to the same block, same let us say their memory address is belonging to the same set, then the only way I can replace this is by removing this 3 and adding this 4. This is the only replacement method used in direct map. There is no other choice which is needed here. Okay, but when I am talking about associative caches, that is set associative caches, eviction, there is some choice which is required. That is, in set associative and fully associative cache, the cache must choose which block to evict when a cache set is full. So that means we know we have to decide in associative, set associative, fully associative, we may have a doubt because there are different ways in which it is arranged. There are, if you see, I will show you a diagram. So you can see here the way 0 and way 1. So if in way 0, let's say one data come, then the next data is coming to way 1. Now another data is coming and let us say that also belongs. So that means this both memory address 4 and 24 both are belonging to set 1. But in set associative there are two ways. So therefore I can put 4 in here and 24 in here. Now what happened, let's say another data come which also belong to, let's say set 1 itself. Okay, we are talking about another data which is also belonging to set 1. So if that address, let's say that address is X, that is also belonging to set 1, any one of this has to be removed. Now there is a choice, either we can remove this or either we can remove this. So we have to think what we have to remove. So in that case there is a choice. In direct map there is no choice, right? But here you can see there are two choices where we will remove. So we will use a replacement policy to decide in which way, whether you remove from way 0 or whether you remove from way 1. Then we use a replacement policy in this case. Okay, in this case the policy will decide which one you have to remove. Now, temporal locality, we know, is the observation that if you access something recently, you are likely to access it again. Therefore, the block you haven't used in the longest time is the least likely to be needed soon, making it the best candidate for eviction. So, here, temporal locality, we know, the principle of temporal locality means what? The best choice is to evict the least recently used block. Temporal locality says that the most recently used, there is a chance that we are using that again, most recently. So according to the principle of temporal locality, we will use LRU replacement, that is least recently used block. We will remove, which is evict, the block which is least recently used. And that idea is coming from which principle? On the principle of temporal locality. So in LRU policy, what we will do is that we will remove that which is least recently used. When eviction is needed, the block that was accessed the longest time ago would be replaced. That means if you consider here, first I put 0x4 here, right, and the second I put 0x24. So which is least recently used? 0x24 I have just used it right now. Least recently used is 0x4. So now if I come another data, that was 54, which also belongs to set 1. Now this 54 will go to what? Way 0, because here this is least recently used. This is LRU policy. This is what do we mean by LRU policy. So here there is a use bit. That is, in two-way set associative cache, a use bit U indicates which way within a set was least recently used. A two-way set has exactly two blocks, way 0, way 1. The LRU with just two options, only one bit is like U equal to 0 means way 0 has least recently used. U equal to 1 means way 1 has least recently used. So here if you see U is equal to 1 means U is equal to 1 means way 1 has least recently used. That is what U is equal to 1 means, right? U is equal to 1 means way 1 was least recently used. So evict way 1. That is it, what it means. And U equal to 0 means use bit it is. Way 0 was least recently used. So evict way 0. Whenever way 0 is accessed, so we will update here. Actually we are updating the use bit. Whenever way 0 is accessed, we will set U is equal to 1, meaning way 1 is now recently used. Whenever way 1 we will set U equal to 0, meaning way 0 is least recently used. So if there are more ways, tracking this least recently used is very much complicated. So it's kind of complex. So maintaining a precise LRU order signifies significant hardware, many bits and complex updated log every time when we wanted to access. Complex hardware and all would be required. So what happened is that in such cases, what we will do to simplify this problem, the ways are often divided into two groups, and U indicates which group of the way was least recently used. Which group is least recently used is denoted by this U. So here U is 0. That means way 0 is least recently used. Okay, I just look way V1. So U equal to 0 means way 0 is least recently used. So we will put way 0 later. And now what happened? Way 1 is least recently used, because now I have updated way 0. So that means U becomes now 1, because what? Way 1 is now least recently used. So that you have to understand. Okay, now there is some problem, some complexity problem. That is, when lot of ways are coming, this would result in lot of hardwares, lot of complex logic would be there. We have to maintain a very large LRU order. So in order to prevent that, the main solution here is that to simplify this problem, we will divide the ways are often divided into two groups, and you indicate which group of the ways was least recently used. Instead of tracking exact order, the ways are split into two groups. We will split the way. Okay, way 0, way 1 in one group. If it is 4-way set, then we will divide into two groups. Group A is LRU, or you just says that now there is a U which will track whether group A is least recently used or whether group B is least recently used. This is used when you have pseudo-LRU, that is when you have complex LRU. So this is how this problem is basically solved. Okay, now let's understand here. Such a policy, that is pseudo-LRU, and is good enough in practice. This approach is called as pseudo-LRU because it approximate LRU without being exact. In practice, it performs nearly as well as true LRU while performing requiring for less hardware complexity. So this is like pseudo-LRU. This type of hardware where you're dividing this LRU into two groups, and then you would decide whether you have to choose whether group A is least recently used or group B is least recently used. This is pseudo-LRU. This would perform just like the true LRU. It's like approximating the true LRU is what pseudo-LRU actually basically doing. But it can reduce the hardware complexity. That is the main advantage of using pseudo-LRU. They will do what? They will reduce the hardware. Okay. So in direct mapping, these are just the replacement policies that can be used. In direct mapping, there is no choices. Two-way set associative can use true LRU method. One use bit is used here. Now, n-way would decide there are a lot of n value can be very large. So we use what? Pseudo-LRU method. So when I'm using pseudo-LRU method, what happen is here is that one use bit will be there for each group to decide whether here in total in true LRU what happened is that totally only one use bit will be there, but in pseudo LRU each group has a use bit. Understand? Now fully associative can use both true LRU also pseudo LRU also as the replacement policy. But the hardware of fully associative we have already discussed in previous condition also, previous lecture also, while we are discussing fully associative. The hardware of fully associative is very complex. Now there is a LRU replacement question. Show the contents of an 8-word two-way set associative cache after executing this following code. So this is an 8-word two-way set associative cache and we are doing this code in here. So we are loading 0x4, 0x24 and 0x54 here. So two-way set associative means it's an 8-word two-way. N is equal to 2. 8-word means what? 2 raised to, that is number of blocks here is blocks is 8. That is what it means. So number of set would be what? 8 divided by 2, that is 4 set will be there. Each containing what? N equal to 2 means 2 ways will be there in each of the block. Now we have understood how it is. So that means now 4 when I am looking at them, now this is a two-way set associative and the number of set is 4. If the number of set is 4, it means it is 2 raised to 2. So set bits are, set index bit would be 2. So in 4 if you take the 0 0 1 0 0 0 like that, how so many zeros would be the 4's binary form. So this 2 bit represent byte offset and 1 0 represent the set. So this would means what? Set 1 it belongs to. Now 24 if you consider again, 0 0 1 0 for 4 and 2 would come as 0 1 0 0, a lot of zeros like this. So here also byte offset 1 0, this is also going in set 1 itself. And 54 if you do again, last is 4, this also would go to set 1, right? So all of them are going to what? Set 1. And in set 1 there is only 2 ways, way 0 and way 1. So that means if you see here, first what happened in way 0, this address go, 4 address go, and then in set 1's way 1 this address is gone, 0x24, which is least recently used. Use value would be 0. Way 0 is least recently used because this is first we have used, then later we have used. So right now I am mostly using 24, right? Fine. Now I need to add 54. So according to LRU policy, least recently used would be replaced. That means way 0 would be replaced. So now way 0 is replaced and U bit becomes 1 because now way 1 becomes what? Least recently used. So this is how you will do the question in LRU replacement. So I hope you have understood. Thank you.